Dr. Sen. Now I request Dr. Sen to please enlighten us with his words. Thank you. Thank you, sir. Over to you.
So thank you, Professor Sharma, for the
Thank you, sir.
introduction. So let us start the session. So as Professor Sharma has mentioned, the title of the session is CFD Principles and Practices. So this is an introductory session where I shall define what is CFD, what is its use, what are the different competing methods other than CFD, and what are the elementary topics for this CFD. So I share one set of slides first. So I shall depict those pages and then I shall go for another set of slides. So first we go, what is the use of CFD? Why it is used? So CFD it is an acronym. So this is a very popular subject in recent time. So this is a numerical tool. So around 1950s or late 1950s, the concept of numerical methods, these were introduced for solving heat transfer and fluid flow problems. So the fluid dynamic problems, the problems on fluid dynamics and heat transfer, there we every day encounter those cases, and the experimental approach, this is the oldest approach for solving heat transfer and fluid flow problems. So such problems are found, suppose if we give the examples of certain problems, that in turbo machinery, in metal casting, in blood flow, in geophysical flows, suppose in atmospheric turbulence, cloud turbulence, groundwater flow, in multi-phase flow, in power plants, nuclear reactions, nuclear reactors, and in aerodynamics, suppose if we go for fluid structure interactions, if we go for black body aerodynamics. So there are so many examples here. We encounter the fluid dynamics and heat transfer. So there are three basic approaches for solving this kind of problems. The problems which I am mentioning here, there are three approaches. These approaches are known as the experimental approach, the analytical or theoretical approach, and the computational approach. So the experimental approach, this is the oldest approach. In experimental approach, what people used to do, they used to make a model. Whatever is happening in nature, they used to try to simulate it in a laboratory. So an experimental setup will be developed and the experiment will be conducted to find out the flow. So in a fluid dynamics problems, the unknowns are velocity, pressure, and temperature. So for a problem, we want the distribution. You know that we use the Eulerian approach in fluid mechanics. So for Eulerian approach, we go for the point approach where we need to find out the distribution of velocity, pressure, temperature, etc. at individual points as a function of time. So these are the solutions of a fluid dynamics problems. In experimental approach, people used to solve this in a laboratory, and this is the oldest approach and a successful approach. It gives high accuracy solutions for a flow problem. Now, there are some limitations with the experimental approach. Suppose an experimental approach, for repetition, it may be expensive. Some equipment for the experiments, those may be expensive. For conducting the experiment, we need expert people. Those expert people may not be available always. Okay. And for very complicated flow, getting highly accurate solutions from experimental approach may not be possible. So experimental approach is a very reliable tool, but it also has certain limitations. And in experimental approach, we don't need any governing equation. So the particular problem of flow or heat transfer, it is governed by certain laws of nature, but those laws of nature we don't require when we go for the experimental approach. So every fluid dynamics problem which is a fluid flow of any kind of fluid, internal flow, external flow, heat transfer, this can be represented by a governing equation. So this governing equation is not required, as I have mentioned, in the experimental approach. So this governing equation will be a partial differential equation in generic form. Okay. So there are some conservation rules: conservation of mass, conservation of linear momentum, and conservation of energy. So these conservation equations all are the partial differential equations. These equations are written at a point as a function of time. So I am just showing one sample equation. So suppose this particular equation which I am showing, this is one set of partial differential equation. This is a generic partial differential equation for the conservation equation. So this we shall discuss again. Before doing that, let us go for the preliminaries. So in experimental approach, we need not deal with such equations. When we go for the theoretical approach of solving a fluid dynamics problem, or when we go for the computational approach for solving a fluid dynamics problem, then we have to handle this set of equation. Okay. Now, when we go for the theoretical approach, the problem is that in this governing equation, there are four types of terms. So all the governing equations in fluid flow or heat transfer, they will have only four types of terms at most. So these terms are, this is known as the unsteady term, this is known as the convective term, this is known as the diffusion term, and this is known as the source term. Okay. So unsteady plus convection equals to diffusion plus source. In this equation, phi, this symbol phi, this is the unknown quantity. So this phi is known as the transported variable, or this is also known as the degree of freedom. This is the unknown quantity. So we want to find out phi at different points in the flow field, okay, as a continuous function of time. Now, when we write this equation, this is a differential equation. This equation also can have an integral form. So the conservation of mass, conservation of momentum, or conservation of energy, they can be written in differential equation format, or they can be written in integral equation format. So the format which we are using here, this is written in the differential format. Okay. So this equation, this is a statement of balance of fluxes of this quantity phi. Okay. So as I have mentioned, unsteady term, convection term, diffusion term, and source term. Now, this third term, this term, diffusion term, this is a second order term, and remaining terms are first order terms. So this is a second order partial differential equation. It means that in this equation, there are different derivatives. So derivatives like, if we talk in specific coordinates, del phi, del x, del phi, del y, del 2 phi, del x2, del 2 phi, del y2. So these kind of derivatives, these are part of this equation. It means that this equation is written at a particular point. So that particular point is valid throughout any region in space of the fluid flow. It means that this equation is written at a point, and this point is arbitrary in a fluid domain. Okay. So when we write this equation, we make it sure that the quantity phi, its first derivative and its second derivatives, they are all continuous. Okay. So this is a basic assumption. This must hold true, that this variable phi, this is a continuous function of space and time. It means that phi is itself continuous. Del phi del x and del phi del y, they must be continuous. Del 2 phi del x2 and del 2 phi del y2, they may be discontinuous at certain points. Okay. So by this assumption only, this equation will be valid. Now these equations, this can be solved by direct integration, or may not be solved by direct integration. So in this equation, the second term, this is known as the convection term. This is a nonlinear term. Okay. So the format which you have written, this is known as the conservative form of the governing equation. This is a nonlinear term. So if phi becomes velocity vector u bar, then this term rho u, if phi is equal to u bar, okay? So this boldface u, this represents the velocity vector. So this is a vector. So if phi becomes u, boldface u, then this term becomes rho u, it becomes the momentum flux. So this momentum flux is a vector quantity. It is a tensor quantity. It is a second order tensor quantity. So this momentum flux, in this case, what is happening? We are multiplying u with u because of this is becoming a nonlinear term. So if this is a nonlinear term, we cannot solve this equation analytically. Okay, so because of this presence of this nonlinear term, in 99.99% problems we cannot solve these equations analytically. It means that if we want to solve a fluid flow problem from the governing equations, we have to go for the approximate approach. We cannot integrate this equation mainly because of the nonlinear convective term. If the convective term is zero, then we may be able to solve this equation exactly by direct integration. So if we are able to solve this equation by direct integration, then we say that we are using the theoretical approach or the analytical approach. So you will find that there are very limited examples, very few cases where exact solutions are possible. So suppose you have read about the Couette flow, you have read about the Hagen-Poiseuille flow. If we talk about the fluid dynamics, these are the cases where you have the exact solutions of the momentum equations. Momentum equations are also known as the Navier-Stokes equations. So when the advective terms or the convective terms, when they will become zero, it means that when the fluid will have no acceleration or the fluid is moving at a uniform speed. So this left hand side represents the acceleration term. So if the acceleration term or if the nonlinear terms, if these are zero, in that case only the flow becomes a linear second order partial differential equation, and then we may be able to solve these problems. So as I have just now mentioned, the flow through a pipe problems or flow through a channel like Couette flow, different cases of Couette flow, Hagen-Poiseuille flow, this flow through a circular pipe, or this simply Poiseuille flow, all these are examples where this convective term is zero, so we are able to solve this equation. So this is the theoretical approach. So what is happening that in real life, in almost all the problems where the Reynolds number is not small. So if the Reynolds number of flow, a viscous, all the fluid flow problems, these are real flow problems. So these are viscosity dominated flow problems where viscosity is very powerful. So if it is a viscosity dominated flow, what happens that at very low Reynolds number, if it is a highly viscous flow where the Reynolds number is very small, in that case, this convection term becomes very weak. You can discard it. So for Reynolds number of the order of 1 or of the much less than Reynolds number 1, you can remove this convective term, but in practical cases, always Reynolds number will be large. So we see that most of the flows which we come across, these are turbulent in nature. These are three-dimensional in nature. Okay, so if we go for high Reynolds number laminar flow or in turbulent flow, these convective terms are never zero. It means that we cannot solve this equation by direct integration. So this analytical approach, this is not possible to implement for the real life fluid dynamics problems. So ultimately we are finding that we have to find out a different approach where we have to get very reliable, high accurate solutions, and we can get quick solutions and without much complicacy. Okay. So as I have told, there are two old approaches. One is the experimental approach. That is the oldest approach when people even did not know about the governing equations. Now these governing equations of momentum, suppose these Navier-Stokes equations, they were derived around 1840. So experimental approach is much older compared to that. An analytical approach, it was started only after the governing equations were discovered. Okay, so we need the governing equations, we need the boundary conditions, we need the domain of interest. Then only we can get the analytical solution if the convective terms are zero. So now, as I have mentioned, for all practical problems, the convective terms are never zero. So we want a very high accurate solution. So when we get the analytical solution for such problems, we say that we are having a closed form solution. A closed form solution means we are getting an exact solution. So it means that if you are able, if we are able to integrate this equation directly, it means that in this case, direct integration, it will give us, suppose if I say at a particular point, at a particular time, the value of u will be 5 meter per second. Then by integration, if we get, it is giving you 5 meter per 5 meter per second, then we are getting an exact solution. But if it happens that we are getting a value which is not equals to 5 meter per second, but this is close to 5 meter per second, suppose if it is 4.9 meter per second, or if it is 5 meter per second, then we say that we are getting an approximate solution which is of high accuracy. So approximate solutions of high accuracy. Just excuse me for 1 second, just for two seconds. Just. Okay, thank you. So I was
Hello,
continuing
hello,
at
hello.
yes, yes.
Sir. We are only able to see the first slide.
Actually, I am explaining this equation. So
Okay, okay,
I am in the first slide only. So
okay,
very quickly we shall move to the remaining part. So this is the
okay.
foundation that actually I am trying to explain why CFD is required.
Yes,
So
yes.
this discussion is coming. Okay. So suppose if we say that yes, at a particular point, at a particular time, the velocity is 5 meter per second. We get by integration. Then we say that yes, we are getting the closed form or we are getting the exact solution. So if we are able to integrate this equation as a function of space and time, we shall get an expression of u bar or bold u as a function of x, y, z and time. Okay. So that equation, actually that closed form equation solution, we don't get. Now, if we get a very highly accurate approximate solution at every point in the domain, then those solutions can be used for the real life purposes. So now the need of CFD arises from there, that the limitations of the experimental approach and too much limitations of the theoretical or analytical approach. So there was a need to find out an alternative approach where we can get highly accurate approximate solutions. So the origin of CFD stems from there, where when the digital computer was invented around 1940s, the early versions. Okay. So the numerical approaches, these were already existing. So forward difference, this finite difference method, it was already existing. But when the computer was discovered, even those were slow speed computers. So people started working on writing programs in the early versions, and they tried for solving simplified fluid dynamics problems and to get approximate solutions. So in early days, people tried using the variational methods, and they tried using the finite difference method to get the solutions. So these are under the group of CFD. So by CFD, we mean that we are solving the fluid dynamics problems by using computations. So by using calculations, by writing program. So when we talk about CFD, we imply that we are using a computer program, we are writing a computer program, or we are using a software which is a commercial software. So by using commercial softwares or by using programs, we are solving practically any fluid dynamics problems of any scale simply in a digital computer in a reasonable time and with excellent accuracy. So the accuracy of CFD, it has established CFD as a very powerful tool. Now this is the leading tool actually. I can say that CFD is a very prominent tool for solving all the fluid dynamics problems of interest. So let us go back to the definition of CFD. So here, just what I was telling now, that all fluid dynamics problems can be solved by experimental, theoretical, or analytical, and numerical or computational approach. So I have highlighted this separately. This numerical or computational approach, this is known as the CFD. So this theoretical and analytical approach, this is valid only for very limited cases. So practically it is not valid actually. So only for theoretical knowledge, some cases. So either you have to go for experimental approach or you have to go for the numerical approach. But you have to remember the solutions which we get by using CFD, these are approximate solutions. These you have to remember, these are not exact solutions. So suppose this is the exact equation, this is known as the continuum equation. By continuum equation, you must know about the fluid continuum. By fluid continuum, we mean continuous mass. So we say that in a computational domain where this equation is valid everywhere, fluid mass is present. If the fluid mass is present at every point, then only the velocity, temperature, pressure, they will be present and then they will be continuous. Okay. So if it is a continuum, if it is working in a continuum, then we say that the equation which we are writing, that is a continuum equation. Okay. Now, when we are using CFD, we modify this equation, this continuum or the exact equation, this is converted to approximate equation. Since we approximate the equation, we approximate the boundary conditions, initial conditions, and also we approximate the governing computational domain. Because of that, the solutions which we generate after solving this particular problem, the solutions also become the approximate solutions, but of high accuracy. So let us very quickly go to the definition of CFD. So we are telling that CFD is a numerical or computational approach where the conservation equations are solved approximately by implementing certain algorithms, okay, in a digital computer. So a computer is compulsory in a CFD problem, and then this is calculating, we are giving the computer certain instructions for performing certain numerical calculations, numerical steps, and then we get high accurate approximate solutions, and that is CFD. Okay. So the unknowns in CFD problems are velocity, pressure, and temperature. So when we say that yes, we are solving a CFD problem, actually what we are doing, we are trying to find out the distribution of velocity, the distribution of pressure, and the distribution of temperature with respect to space and time. So velocity, pressure, temperature, fields, we are trying to find out. And these are some of the examples where we can use CFD or experiments. These are just very few examples, and CFD, it is too much diverse. Now it is a very strong branch. It is now, you can say that around 70 years old. So it has developed a lot. Practically any fluid dynamics problems we can solve by using CFD. With increasing time, the computers are becoming very powerful in terms of the speed and the memory. So the calculations of high speed, this high Reynolds number turbulent flow, which we could not imagine before, those are also becoming possible nowadays. Okay. So let us very quickly move to this governing equation. So this is the equation for this unknown phi. This phi can be velocity, this phi can be temperature, or it phi can be any other quantity. So this nabla, this is an operator. Okay. This is known as the del operator. So this is del dot, this is a dot product, and this is the diffusion coefficient. So if we consider, so any equation, if you talk about this conservation of mass, that is known as the continuity equation. If you think of the conservation of linear momentum, or if you think of conservation of energy, all the equations are special cases of this particular equation. So this is the root of all the equations. Okay. So let us find out that how will we derive the continuity equation from here. So if we want to derive the continuity equation for mass conservation, so we shall take this phi is an intensive property. Okay. So intensive property means it is independent of the mass of the system. So if we put phi equals to 1, and if we say that there is no source of mass, so this is a source term. So S stands for source. If there is no source of mass or no sink of mass, mass is neither created or destroyed, then this term will be 0. So we get from here, we put rho equals to 1, means we put phi equals to 1 here, we put phi equals to 1 here, we put phi equals to 1 here, and we put 0. Then what we get, if we put phi equals to 1, this is the gradient of 1. Okay. By gradient we mean del del x, del del y, del del z terms are present here. So this term will be 0. Gradient of 1, gradient of a constant, it will be 0. So right hand side will be 0, and we have already put phi equals to 1. So this unsteady term, it will be del rho del t. So we are getting like del rho del t plus divergence. This is the divergence operator. Okay. This is the divergence operator del dot. So divergence of rho boldface u into 1. So divergence of rho u. So if you see here, del rho del t plus divergence of rho u equals to 0. And if you remember, this is the continuity equation in the strong conservative form. So this is also known as the generalized continuity equation in the vector form. So I just skip this point to inform that this particular equation, this is a vector equation. We say that this is a coordinate free equation. So we don't say that this equation is written in Cartesian coordinate system or cylindrical or spherical coordinate system. This is independent of coordinate system. So this is a vector equation. So every term will be a vector. Okay. So this is a vector quantity. This is these vector operators are present, and this is, it may also have individual components. Okay. And this will also, if it is a vector, if it is a vector, it will also have individual components. So overall, this is a vector or coordinate free equation. Similarly, we can derive the momentum equation from this case. So uh, many of you are aware about the Reynolds transport theorem. In Reynolds transport theorem, when we derive the governing equations by using the Reynolds transport theorem, we take capital phi as the extensive property, and small phi we take it, define it as small phi equals to d capital phi d mass dm, d phi dm. So in case of the momentum equation, this small phi, the intensive property, it is equals to small u. Okay. So for the momentum equation, phi becomes small u, and this is the diffusion coefficient. Coefficient of diffusion, it means it must be dynamic viscosity. So when gamma becomes the dynamic viscosity, and the source term, it becomes the pressure gradient. So minus grad p, this is the source term. So in this case, what happens, if you put that phi equals to u bar, phi equals to boldface u, then this unsteady term is del del t of rho u plus divergence of rho boldface u into, again phi means this is boldface u, so this is divergence of rho boldface u, boldface u. So this is the momentum flux. So this is a second order tensor. So we are taking divergence of a second order tensor. So it becomes a vector quantity equals to divergence of this term, divergence of, this is viscosity mu grad into gradient, grad of velocity vector. So this term is divergence of mu grad u, boldface u, and this source term, this is minus gradient of p. So this becomes minus gradient of p. So if you remember, this is the Navier, this represents the Navier-Stokes equations in the vector format. Okay. Similarly, we can get the energy equation from this basic equation. So let us move first. Now, when we go for the CFD, we use a term discretization. So discretization, I shall discuss it later. I have another set of slides. First, we quickly cover this part. Then we shall move to the second slide, second set of slides. So there we shall discuss what is the meaning of discretization. So this discretization, this is the backbone of a CFD problem. So this is the original equation. This is the continuum equation. This continuum equation is converted by discretization into approximate equations. These approximate equations, they are certain kind of algebraic equations. These algebraic equations can be linear. So if this is a nonlinear equation, the approximate equations will also be nonlinear. Okay. So in basic discretization, there are three foundation methods. So in CFD, for a fluid dynamics problems or for a heat transfer problem, there are three basic fundamental methods. These methods are used, and this is the oldest method, the finite difference method. This is the oldest method for solving the fluid dynamics problems. And next came the finite volume method. And finally, we got the finite element method. So around 1970s, this finite element method, it was originally being used for solid dynamics problems. Around 1970s, people were trying to implement the finite element method for the fluid dynamics problems. They got some problems because of these convective terms. Because of this term, then they found some solutions and they started using the FEM also for the fluid dynamics problems. So these are the three foundations of the CFD solution techniques. Now, if you go for solving this generic transport equation, so this is a transport equation for the transport of this quantity phi, transport of phi by convection, transport of phi by diffusion. So this gamma is the diffusion coefficient and this u is the convective velocity. So this velocity will be responsible for convection of this quantity phi, and this diffusion, this is like conduction. Okay, so this diffusion coefficient, this will be responsible for the diffusion transport of this property phi. So when you write finite FDM, FVM or FEM, there are two basic approaches for handling the governing equation. This governing equation, the original equation in this original format, in the exact format, this is known as the strong form of the governing equation. Okay, so this original PD is known as the strong form of the PD. So the two approaches are the, one is the direct approximation of the strong form. So we start the approximation directly from the original version or from the strong form. This approach is known as the finite difference method or FDM. So it means that if you look into this equation, suppose this is a second order equation. Okay, so let us consider a simple example. Suppose we are just telling the Laplace equation, Poisson equation of heat conduction in one dimension, d2t dx2 plus 1 equals to 0. So suppose if I ask just as, let us say,
Subhankar sir, some voice problem are there. Hello.
Hello.
Yeah.
Please wait for few minutes.
Yeah. Yeah.
Hello? 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 Hello?
I don't know how did it happen. So it happened when, now only or long back?
Hello.
Just now. Acha. Okay. Okay. Sorry for the
Yes,
interruption.
sir.
Am I audible now?
Yes, yes, you are audible, sir.
Okay. Okay. So I am
Please,
disconnected. Huh? Okay.
please continue, sir. No problem.
Okay. Thank you. Thank you. Just 1 minute. So let us continue from where we ended, from where we stopped. So as I was telling, all the discretization techniques, these are actually numerical integration method. So CFD is a numerical integration of the governing equation. Since the governing equations are functions of space and time, so if we look into this equation, there are two types of variables. One set is dependent variable or the unknown, other set is of the independent variables. So by dependent variable, we mean velocity, pressure and temperature. By independent variable, we mean space and time. Space means x, y, z and time is t. So here we are classifying these discretization techniques. We are just these approaches we are discussing here. So there are two foundations, that direct integration of the direct approximation of the strong form. So we start the approximation directly from the original equation. We don't integrate it explicitly. So if we do that, then we say that we are using the finite difference method. So this is the most straightforward approach, and this is the simplest approach of solving a fluid dynamics problem. And this is the oldest approach, but very powerful approach. It is very reliable. It gives very high accurate solutions. So only if there is a complicated geometry where the domain is not regular in shape, then there is some difficulty, but still it gives good results. So this is a very powerful tool. And the other two methods, like finite volume and the finite element method, they are dependent on the direct integration of the governing equation. So what we do in these two approaches, this approach FVM and FEM, we directly integrate the governing equation. After integration, we get certain simplifications. Okay, so those things are, we shall not discuss in details. Just we mention there that in this integration approach of governing equations, we define a weight function. Okay, so the integration methods of CFD, they use a weight function. The value of the weight function, it is changed, it is ranging between 0 and 1. In the finite volume method, we take the weight function to be always 1. In finite element method, we don't force it, so we allow it to vary between 0 and 1. Since in finite volume, we force it to be 1 always, because of that, we get some less accuracy in finite volume method compared to the finite element method for the same problem. Okay, so we can say that this finite volume method, this is a special case of the finite element method. So just briefly, I mentioned the classifications, the differences between FDM, FVM and FEM. So this FDM, it cannot be used on the unstructured grid. Okay, so there are two types of basic meshes. These meshes for solving the problem, the approximation of the domain, this is known as mesh generation or grid generation. There are two basic kinds of grids. One set is known as the structured grid. One set is known as the unstructured grid. By structure, we say that there is a specific structure. There is an organization in the grid formation. So by grid, we can say that suppose there is a square. So if you make parallel lines, so you divide the square into 4 axes. Okay, we say that we are getting a grid of the small squares. So we are getting a grid of cells and we are getting so many grid lines. Okay. So these straight lines or curved lines, these are known as the grid lines. In case of structured mesh, we can identify the grid lines. So it is difficult, I understand it is difficult to visualize from discussion. If I would have a picture, it could be easy to explain. So just let us explain it still now, still like that also, that finite difference method does not operate on an unstructured grid. It needs a structured grid. This is a compulsory requirement. And for finite volume method, it operates on a structured mesh or also on unstructured mesh, and same for the finite element method. Okay. So basic difference is that finite difference directly operates on the equation, but in finite volume and finite element, we integrate the governing equation. Okay. And finite volume method is a special case of the finite element method. Okay. So now we are showing the steps in solving a CFD problem. So when we talk about a CFD problem, what are the requirements? Okay. So first we need the governing equation. It means that we need the governing equation like this. This is the basic requirement. We need a computational domain. We need the boundary conditions. We need the initial conditions. Okay. Now there are different kinds of problems. Okay. So in a CFD problem, we may require the boundary conditions. We may require the initial conditions, or we may require boundary and initial conditions both. Based on this, we classify the problems in three types: IVP or initial value problem, BVP or boundary value problem, or IBVP, initial boundary value problem. So very briefly, let us just define initial value problem. These are known as the marching problems. So I have another set of slide. Very quickly, I shall cover what is a marching problem, what is an equilibrium problem. So by marching problem, we say that this is an initial value problem where we need an initial condition for solution of this problem. So this will be either parabolic type partial differential equation or hyperbolic type of partial differential equation. Boundary value problem we solve in a closed domain. So in initial value problem, we solve it in an open domain. By open domain, what do we mean? We shall discuss it. So in boundary value problem, we need a closed domain. So boundary conditions must be specified at the boundary of the computational domain. So such problems are known as equilibrium problems or jury problems. So these equations, these boundary value problems, they show the elliptic behavior. So what is the meaning of parabolic, elliptic, hyperbolic? I shall discuss it. And then there are mixed type, elliptic and parabolic behavior. Then we discretize the domain. So when we talk about discretization, what we do, as I have told, that this governing equation, this is a continuum equation. Continuum means it is valid everywhere. So if we think of a continuum, if you think of a domain, domain means a region where the fluid flow where the fluid is flowing. In a flowing domain, in a flowing region, you can select a part in space. There you want to solve this problem. So with that particular region, we define as the domain. So at every point of the domain, this equation is valid. By every point, I want to say that if you take 2 points, the distance between these 2 points is less than epsilon. So we say that the distance between 2 points is infinitely small, that is infinitesimal. Then also, this equation is valid at all points. So even in a small domain, this equation is valid for, you cannot say by million or billion or trillion, it is infinite number of points. So this is infinite. Because of that, we say this is a continuum equation. By discretization, what we do, we break this continuum behavior of this equation and also of the domain. By discretization, we imply we don't want this equation to write at all points. We want to write this equation only at discrete points. So we don't need the continuum behavior, but we need the discrete behavior where we want to write this equation at finite number of points, at pre-selected points. These points are known as the nodal points. So those points are pre-selected. They are finite always. So a computer, it cannot handle infinite number. So a computer is the machine of finite accuracy. So it will handle only finite number of, it can only handle finite number of equations. But when we go for the exact solution or the theoretical solution, we don't talk about finite, we talk about infinite. So whatever the value of x, y, z you will put, you will get the solution. So this is the big difference with CFD and the theoretical approach. In theoretical approach, you need the solution everywhere. But in CFD, we say that no, we don't need the solution everywhere. So if the distance between 2 points, if it is a finite distance, then also my solution is acceptable. So I repeat this portion. When we go for the theoretical approach, in a continuum approach, then we say that the distance between 2 points where I want to write this equation, this distance is infinitely small. So this is less than epsilon, or this is of the order of epsilon. But when we go for a finite problem, we say that yes, we need that, we want to write this equation. We write this equation at many points such that the minimum distance between these 2 points where you want to write this equation, there should be maybe 0.01 or 0.001. So this 0.001 or 0.01, this is a finite number which we can perceive, which we can understand, and this is much larger than epsilon. So this continuum concept, this is broken by discretization. So we don't need solutions at all points. We need solutions only at pre-selected finite number of points. Because of finiteness of this problem, we say finite difference, finite volume, finite element. If it is infinite, then we go for the this analytical approach or the theoretical approach. So let us come back to the steps of the CFD problem. First, we identify the problem, that this is of which kind of problem. Is this a marching problem, or is it an equilibrium problem? Whatever it is, we need the boundary conditions, initial conditions, or both, depending on the nature. Then we generate the grid. So when we discretize, we have to discretize the governing equation, the boundary condition, the initial condition, and we have to discretize the computational domain. Discretize means this continuous nature, we have to convert it to discontinuous nature. So we have to introduce discontinuity. That is discretization. So by generation of mesh or grid, what we do? A domain which is a continuous domain, which is that domain, now we divide into small segments, into small subdomains. By generating small subdomains, we introduce many nodal points where the grid lines intersect. At those nodal points, we write the approximate equations and we solve these equations. Okay. So after making the mesh or grid, we select the discretization basic techniques, such as we can use finite difference, we can use finite volume, we can use finite element. So there is no hard and fast rule that you have to use finite difference or finite volume or finite element. All of these are powerful, and these methods are giving very comparable results. So you can use any of them. So mostly finite volume is used for the fluid dynamics problems in recent time, and FEM is also being used. So FEM is used where there is fluid and solid both. So if there is some fluid and solid interaction, then we go for FEM. And in finite difference, for simplified problems, we go for finite difference. But finite difference is a very powerful tool, even though it is an old approach. Then, based on the governing equations, whether you have the CFD problem, it can involve only one governing equation or it can involve multiple governing equations. Now, based on that, these equations will be converted to approximate equations. These approximate equations will be either linear or they have to be linearized algebraic equations. So this is a very important step. So this set of equations, these are known as the approximate equations. So when you have the original equation before discretization, that is the generic equation or the continuum equation. Now that you have to write at every discrete point, the points you are generating in this step, These points are known as the nodal points. So based on these discretization methods, this nodal, you will write algebraic equations. So the partial differential equation or the ordinary differential equation, it will be converted to algebraic equation. This conversion method is known as discretization. So getting the algebraic equations, what is an algebraic equation? We say that yes, 2x plus 5y equals to 7. This is an algebraic equation. It is having two unknowns, x and y. Okay. So if you have n number of unknowns, so it will give you a square matrix system of size n by n. Now, conversion of the continuum problem to the algebraic equation setup problem. This is known as the discretization, and these three are the popular tools for discretization. Now, your original differential equation, it may be linear, it may be non-linear. So if the original differential equation is linear, these algebraic equations will become automatically linear. If your original equation is non-linear, then your algebraic equations will also be non-linear. But what we do, we make these equations linear before solving. So we say that it is linearized algebraic equations. So if we just say that we have the partial differential equations, then this step is known as the ax equal to b step. Okay. This equation is converted to so many equations that it gives a system of linear algebraic equations represented by capital A small x equals to small b, where capital A is the coefficient matrix. This is a known matrix, where x is the unknown vector and b is the vector from the boundary conditions and the initial conditions. Then we solve these equations by direct method or by iterative method. So this matrix equation system up to this much is the CFD approach. Okay. So starting from this problem up to generation of the governing equations, this portion is known as CFD. Okay. After you get this ax equals to b system, then you can solve this x from x equals to b. X will be a inverse b by direct methods or by iterative methods. So we have linear equation solvers. So suppose you are solving you are using Gauss elimination method, Gauss-Seidel method. These are the two examples of direct methods or iterative methods. Now, these are used only for the linear equations. Okay. So if you want to use Gauss elimination is only operating on the linear matrix. So by linear matrix, what do we mean? Suppose we are writing the matrix ax equals to b. If this coefficient matrix A is not a function of the unknown x, then the matrix system is linear. So when we are solving Gauss elimination, we are using a linear matrix equations. Because of that, we have to linearize these equations. Okay. But if it is non-linear, then also it can be solved. But the conventional approach is that we linearize the governing equation, then we implement the linear equation solvers, maybe direct method or maybe iterative method for solving the matrix system. Mostly we go for the iterative methods, because if it is a direct method, it will have some memory problems. It will be slow. So calculations will be slow and you have to store so much data. Okay. So it will be just mostly all the CFD solvers, they will go for the iterative solutions. Actually, these CFD problems are non-linear, and non-linearity is handled by the iterations. So we go for the iterative approach. So when we solve it, by solving, we get velocity, pressure, and temperature. So final step is the post-processing. By post-processing, we mean that if we know temperature, we can calculate the heat flux, we can calculate the maximum amount of, suppose if you know the heat flux, then you can calculate the Nusselt number, okay, the distribution of Nusselt number. Similarly, if you have the velocity distribution of pressure, you can calculate the normal stresses, you can calculate the shear stresses, you can calculate the drag force, lift force, the moment, etc., etc., by calculation of the data obtained from momentum equations. So this step is known as the post-processing. Okay. So this is briefly the outline in a CFD solver. So by solver, we mean that how are we generating this ax equals to b from the differential equation. This step is known as the CFD solver. Okay. So CFD solver is different and matrix equation solver, that is different. So here also we use solver. That is a different thing. Okay. It may be Gauss elimination, it may be Jacobi, it may be Gauss-Seidel, it can be Gauss-Jordan. These are matrix equation solvers. And when we talk about I am using a CFD solver, we mean that the discretization method, yes, we have the differential equation, and how are we generating, how are we converting the differential equation to algebraic equations. So that is the function of a solver. So here, in terms of FEM calculations, we need some formulas. So these are not required. So I am skipping this. So very quickly, I am showing in another some other topics which are not discussed. I shall just after very quickly I highlight something for finite difference steps. Then I shall go back to the remaining parts. Okay. So I am directly showing one particular problem of solving a temperature distribution in a rod by using the finite difference method, finite volume method, and finite element method. So we shall solve the one-dimensional Poisson equation subject to the Dirichlet boundary conditions. Okay. So this is an equilibrium problem, an elliptic partial differential equation, Poisson's equation. This is the Poisson equation. K is the thermal conductivity, T is the temperature, okay, and this Q is the heat source. So here Q is given 1 and thermal conductivity is 1, and this is the computational domain. This is the physical domain. Physical domain will be converted to the computational domain. So in this particular problem, this is a simple linear equation. This is a linear equation. There is no movement of this rod. Okay, there is no flow around this rod. Because there is no flow of air around this rod, we are not considering any heat transfer by convection. It is only heat transfer due to conduction within the rod. Because of that, this advection terms are zero and it has become a linear equation. So this has become, since it is a one-dimensional problem, this has become an ordinary differential equation. So it is not del, it has become d. There is no y, it is only a function of x. So temperature is a function of x. So you can now, you have been given at x equals to 0, t is given, at x equals to 1, t is given. So you have two boundary conditions and you have the second order equation. So you can easily calculate this integration constants, and this is the solution of this temperature distribution. So this is the parabolic distribution of temperature, ax square plus bx plus c kind of distribution. Okay. So here, this is an elliptic partial differential equation. So for elliptic partial differential equations or equilibrium problems, so this is the boundary value problem. So I was just classifying the equations in different types: initial value problem, boundary value problem, and the mixed type. So boundary value problems, they are known as the equilibrium problem and they show elliptic behavior. Okay. So this Laplace equation or Poisson equation, they correspond to the boundary value problems. So you need the boundary conditions at these two boundaries. So because of that, we are giving these boundary conditions, and this is the equilibrium problem. This you can easily integrate and you are getting the solution. So this solution is known as the exact solution or the analytical solution. So since this is a linear ordinary differential equation, we are able to solve it. Okay, and we are getting the exact solution. Now, if we want to use CFD, we shall get the approximate solutions. So we can use finite difference method, we can use FVM, or we can use FEM. So I shall briefly discuss the implementation of the finite difference method. Okay, what we do, this is the continuous domain. This domain we shall split and we shall make it a discontinuous domain. So we shall just discretize this domain the way. So this problem will make the concept clear that we have to discretize each and every quantity. We don't need any initial condition. So this is the boundary value problem. There is no time derivative. So if the time derivative is absent, we don't need any initial condition. We need only the boundary condition. Okay, because this is a boundary value problem. So here, this was the rod. Now we are dividing the rod length. The entire length was 1 into 5 segments. Okay. So if we starting from x equals to 0 to x equals to 1, we are splitting the rod into 5 segments. 5 segments introduces 6 nodes. So we have these small circles. These are known as the nodes. Okay. So we have 6 nodes. Now this particular step, this continuous domain is discretized into subdomains. So this is a subdomain. Okay. In finite difference, this intermediate zone has not important. It has no importance. Only this length is important. Okay. So only these are the nodes. These small circles. These are the nodal points. Okay. So we shall discretize the governing equation and write it at the nodal points, and then we shall generate the system of equations and we shall solve it. So let us show what have we done. Now this particular segment distance, this is known as the grid size or the mesh size. So grid and mesh, they represent the same thing. Conventionally, we use the word grid in finite difference. We don't use grid in finite, mesh in finite difference. We say finite volume mesh or finite element mesh. In finite difference, we don't use mesh, we say it is a grid. So this delta x, this is known as the grid size, and we have generated a uniform grid. So this is a uniform grid of 0.2 size. So the unknowns are T2, T3, T4, and T5. So T1 and T6, these are given at the boundary conditions, and all the boundary conditions or the initial conditions, these are exact solutions of the governing equation. So suppose if you look into the original problem, these are given solutions. So these are the exact solutions of this equation. Okay. Now approximate solutions at these 4 points we have to calculate at point 2, 3, 4, and 5. Now, as I have told, as you know actually, that this Taylor series is the foundation of the finite difference approach. So we are not actually Taylor series part, we are skipping it. There is not much time. So you know it actually that this is a second order term. So this is having an elliptic behavior. What do we mean by that? So if you hit the rod somewhere, suppose if you hit the rod here, what will happen? This heat will be transferred in all the directions. Okay, if you hit here, so this heating effect, it will move in the right side, it will move into the left side. If you cool it down, so both the sides you will have the equal effect of cooling. It means that whatever the perturbation, heating or cooling you implement at a particular point, that will propagate with same intensity in all directions. So this transport of heat diffusion, this is isotropic. Okay, this is the point which I want to say, that the heat transfer by conduction, this is isotropic. This is not function of direction. So heat waves will move in a spherical wave form. Okay, so by that we want to say that an elliptic PD, where we are getting d2t dx2 kind of terms, this you have to discretize by central difference approximation. Okay, so this is the second derivative. This we can approximate by forward difference, you can approximate by backward difference, you can approximate by central difference, but you cannot approximate by forward or backward difference. You have to use the central difference. It means that if you open any textbook, you will find that for this second derivative, there are different approximations available, forward, backward, and central, but it does not mean that you can use any of them. So the discretization scheme, that is known as the discretization scheme, whether you are going to use forward difference or backward difference or central difference, that will be selected based on the nature of the heat transfer. Okay, so heat is being transferred equally in all the directions. So it means that if you take forward difference, you are giving importance only in the forward side. If you use backward difference, you are giving importance only to the backward side. If you are using central difference, you are giving importance in both the directions. In heating or cooling, we give importance in both the directions. Because of this reason, this particular term, you have to by default discretize by using the central difference scheme. So if you use a forward difference scheme or if you use a backward difference scheme, so this choice is non-physical. So if it is a non-physical solution, what will happen? You will get incorrect result. So if you discretize it by forward difference, then also you can discretize it, you will get a matrix, you will get a solution, but those solutions will be meaningless. So in CFD terminology, there is a very popular term known as spurious solution. Spurious means effect. So if it is a spurious solution, it is a result of non-physical discretization. So it means that there are different kinds of terms in a governing equation. These terms you have to discretize based on the nature of that term. So this is a diffusion term. Now, diffusion has the property of elliptic behavior. So diffusion has no preferred direction. Suppose when we go for convection, convection has a preferred direction. So in convection, you have to use backward difference. But if you go for the diffusion, it is independent of direction. It is isotropic. Because of that, you must have to use the central difference scheme for the diffusion. Okay. So if you see the step here, we have done like that only. So we are using the central difference approximation at node I. So I is a generic node which can take the values of 2, 3, 4, and 5. These are the unknown nodes where we don't know the value of the temperature. Okay. So if you discretize it at point I, this is the expression. Okay. Then we put it here in the original equation and simplify. And this is the algebraic equation which we get. So what we do that all the unknown quantities we bring to the left hand side and all the known quantities we bring to the right hand side. Temperatures are unknown, they are coming to the left hand side, and this delta x is a known quantity. This is your mesh size, this is a known quantity, so you are bringing to the right hand side. So this is known as the generic algebraic equation. So which I was telling that the purpose of CFD is to convert the differential equation, this is the differential equation, to set of algebraic equations. So it has already done that. So we are doing this. So and in finite difference there is direct, we are, suppose this is the strong form, this is the strong form of the governing equation. You can see that we are directly operating on this equation and there is no integration symbol available. Okay. So during this step, there is no integration symbol explicitly visible, but still this is integration. Whatever we are doing here, actually we are integrating it. So by putting the Taylor series, actually we are integrating the governing equation. So this is the generic equation where we have to put the values of I from 2 to 5. We can put I equals to 2, I equals to 3, 4, and 5. We shall get the equations and system of equations, and these equations are known as the coupled equations or the simultaneous equations. Okay. So we need 4 equations, and we have 4 unknowns, T2, T3, T4, T5. So how many unknowns you have, those many equations you have to generate. Then only you will have a consistent solution. The equation system, it will be consistent. Okay, let us see what we have done here. First we are putting I equals to 2. By putting I equals to 2, from this generic equation, this is generic equation, we are putting I equals to 2. This is becoming T3, this is becoming minus 2 T2, and this is becoming T1, and we know that this is 0.2. This delta x was 0.2, so it is becoming minus 0.04, and we already have this T1 coming from the boundary condition. It is a known quantity. It is the temperature of the left boundary. So what we do, all the unknown quantities we keep in the left hand side, and all the known quantities we shift them to the right hand side. Okay. So from this nodal point 2, this is the equation. That's minus 2T2 plus T3 equals to minus 100.04. This is the first equation. Now you apply this equation at node 3, node 4, and node 5, and you generate the equations. Okay. So all these equations, if we write together, we get the system of algebraic equations. So this is the matrix equation system, the system of equations which I was telling here. I was telling it here, a single or multiple system of linear or linearized algebraic equations. Okay, this is the end of the CFD step. So if we go back to the problem here, we have 4 equations, 4 nodes, so we have 4 unknowns. So this is the system of matrix equation. Now we have 4 unknowns, we have 4 equations. This is a known matrix, this is a known vector, this is the unknown vector. So we can use Gauss elimination, we can use Gauss Seidel. There are so many methods you can use, and we can solve it. So you remember that this matrix must be a square matrix. So there are four unknowns. It must be a 4 by 4 matrix. So if it is n by 1 vector, it will be n by 1 matrix. So this is a symmetric matrix. Okay, so you see that Aij equals to Aji. This is a symmetric matrix, and this is a banded matrix. Okay, it has three diagonals. So this is the major diagonal, this is the super diagonal, this is the sub diagonal, and remaining terms are zero. So this kind of matrices are known as the sparse matrices. A matrix in which most of the terms will be zero. These are known as the sparse, S-P-A-R-S-E, known as the sparse matrices. So this is an example of a sparse matrix. The beauty of CFD is that it will always generate a sparse matrix. So if you are dealing with a sparse matrix, we should use the iterative methods. In iterative methods, we need not store these zeros. But if you use direct methods, you have to store these zeros. So your computations will be expensive. So it is better not to use a direct method. But for this particular problem, there is one very, you can say, powerful tool that is a basic, that is a modified Gauss elimination method that is known as the Thomas algorithm. This is the modification of the Gauss elimination. So by Thomas algorithm, we can solve this problem with very minimum operation count. Okay, that is specifically designed for the tridiagonal matrix systems. So this matrix has certain properties. It is always a square matrix. It is a banded matrix. It has three diagonals, first diagonal, second and third. So it is tridiagonal. Now these three diagonals put together, they are appearing as a band. Okay, so this kind of band matrix are known as the banded matrices. And since this is a symmetric operator, this del square, this nabla square, del square, this operator, this is a symmetric operator. Since this operator is symmetric, the matrix must be symmetric. So this matrix is also symmetric. Okay, so we are using the Thomas algorithm. We are not showing the implementation. Directly we are showing the results. So these are the temperatures at 4 points. Similarly, very quickly let us pass the finite volume solution. The same problem, if we use by finite volume, we have to integrate this equation. So you see the big difference with finite difference. There is no integration symbol anywhere in finite difference. But when we go for the finite volume method, okay, so finite volume is a special case of the finite element method where we follow the method of weighted residuals. So this MWR, where W is the weight function, which I told in the beginning that for finite volume, we force the weight function to be 1. So there is integration. So in finite volume, there is a little difference in the grid, in the mesh. So we don't say grid, we say it mesh. So this is a cell around a particular nodal point. Okay, this cell size is same of delta x. We integrate the governing equation over the cell face. Okay, between the cell face boundaries. So this is the west boundary, this is the east boundary, and then we generate the generic equation. So if you see here, for doing that, so this is the elementary computational domain, omega E for element. After integration, we generate it. So these are the steps actually. We do some simplification, and finally we get the same equation. So for this particular problem, the finite difference and finite volume, they are giving you the same generic equation, and we are getting the same matrix. Using this Thomas algorithm, we get the solutions. So here is the difference with finite volume difference, that we define a residual. Okay, so sum of the residual in a weighted sense over the entire domain, it will be 0. So by that definition only, we are getting the discretized equation. So here we are showing the finite element solution also. So finite element solution is more involved with mathematics. There are lots of steps. So we don't discuss it. So we skip the finite element solution. So finally we are comparing analytical solutions and the numerical solutions, the approximate solutions. So all the temperatures, we are finding that for a simple problem, the approximate solutions are exactly matching with the analytical solutions. So these are the internal points at 2, 3, 4, and 5. So approximate and exact solutions, they are exactly matching for this simple problem. But if you go for a complicated problem where there are convective terms are present there, you will not get this kind of good match. Okay. So I shall go to the second set of slide. So since the time is not much, very quickly I shall discuss some basic things are not present in this slide. So uh, just hold on. I am changing the slides. So welcome back. Welcome back to this seminar. So this part actually I could not prepare slides because of shortage of time, but this is containing some important discussions. So very quickly I shall cover. So in this particular sketch, I am showing the concept of a computational domain. So this is a region in space where the governing equation is valid. So this portion is known as the domain. So we are separately marking here. This is the domain, this particular region where the equation is valid. This is known as the domain. Generally capital omega, this is the symbol of domain, and this curved portion, this is the boundary. Okay, so this is a closed curve, and this is known as the domain boundary and denoted by the symbol capital gamma. So here we are showing the Poisson's equation valid for this domain, and these are the different kinds of boundary conditions. Okay, so this domain boundary we are splitting into two types. Okay, so this is the Dirichlet portion where we define the temperature. This is an equation for temperature. So where we specify the value of temperature. So this is the part of the Dirichlet boundary, and in the right part, in the second portion, we say that the second portion is insulated. If it is insulated, we say that the heat flux is zero. So it is gradient of T is zero, or del T del N is zero. So this is a Neumann boundary condition, zero heat flux, Neumann boundary condition. Okay. So in our elementary CFD, first we have to classify the governing equations. So there is one standard practice by using a different standard differential equation. We classify the governing equations. Then there are methods of eigenvalues and method of characteristics. So let us very quickly go for the standard differential equation format. So let us consider that this particular equation, it represents a generic second order partial differential equations in two independent variables. We consider a steady state equation. Okay, so this is an equation where this quantity phi is unknown. So x it represents the second derivative. This represents del 2 phi del x2, a, b, c, d, etc., etc. They may be constant or they may be variables with respect to x and y. Okay, so this kind of equations, this is a second order equation. This is containing one mixed derivative, del 2 phi del x del y, del 2 phi del y2, del phi del x, etc. Okay, so there are certain steps. Those steps we are not discussing here. Directly we are going to this derivation, the end of the derivation. So if a governing equation is of this format, now what is the behavior of this equation? Okay, so when we solve the CFD problems, we have to know the mathematical behavior of the problem, that is it a marching problem, or is it a boundary, or is it an equilibrium problem? So is it an initial value problem, or is it a boundary value problem? So that we shall decide based on the outcome of this equation. This outcome will help us to choose which kind of discretization we have to use for the governing equation. Okay, so if we go to the end of this derivation, we are finding that we are defining the discriminant by b square minus 4ac. So there are lots of steps actually here. So those steps actually takes time. within this specified time, it is very difficult to cover this part. So here, this is whatever we get in the analytical geometry. Suppose in 10 plus 2, when we read the analytical geometry, we get the conic section equation. So this conic section, in case of a conic section equation, we define the, based on the discriminant, we define the nature of the curve, whether it is hyperbolic behavior, it is displaying hyperbolic, parabolic or elliptic behavior. Based on the magnitude of this b square minus 4ac term, we define it. Now, this conic section equation, this is the generic conic section equation. It is very similar to the equation which we are writing for the partial differential equation of order 2. Okay. So from here, we get a link that if the discriminant value is positive, okay, so we get two distinct slopes. We get two different characteristics at every point in the fluid domain. So we say that this will represent a hyperbolic partial differential equation. By hyperbolic, what do we mean? So by hyperbolic, we mean that it is a marching problem. So it will be an initial value problem. We may require one initial condition, or we may require two initial conditions. So if b square minus 4ac will be 0, then it is a parabolic partial differential equation. So we say that only one real characteristic will exist. So b square minus 4ac greater than equals to 0, this first condition and the second condition, it will represent that we are dealing with the marching problem. What is the marching problem? In a marching problem, we will be given the initial condition. Knowing the initial condition, we travel in space or time to get the new solution. So how to interpret this? Let us consider flow through a one-dimensional channel. Okay, let us consider, as I am telling, the flow through a channel in one dimension. We want to find out the velocity at different points in the channel. So you consider the x-axis. Okay, you consider the channel as a one-dimensional problem. It is going along the x-axis. What is happening that when x equals to 0, you know the value of the velocity. But when x equals to L, the channel is ending there, but you don't know that velocity. You have to find it. Okay. So what we do in a marching problem, we know the initial condition, then we know the value of velocity at x equals to 0. Using this value, you calculate the value of u velocity at x equals to delta x. Using this value and the previous value, you calculate the u velocity at x equals to 2 delta x. Similarly, you find the u value at x equals to 3 delta x and so on. It means that you continuously travel in space from x equals to 0 towards x equals to L. So in right hand side, really you don't know the solution, but you are actually calculating the solution. So when you are calculating the solution from the old solution, we are actually marching. So in this case, initial condition will start the calculation and it may have the boundary conditions also. So when we move like this, we can move in space or we can move in time. Then we say that we are solving with a marching problem. Now, the last case is pending cases. When the b square minus 4ac, it becomes negative. So in this case, we say that no characteristic exists and we get two imaginary or distinct characteristics. So there is no real characteristic. So in this case, we say that we are dealing with the elliptic partial differential equation. So here we are saying that the partial differential equation, it will be elliptic in nature. So if it is an elliptic partial differential equation, we shall write this equation in a closed domain. We have to give the boundary conditions. In an elliptic partial differential equation, initial conditions are not required. Those are the boundary value problems or the BVPs. So examples of boundary value problems are Laplace equation, Poisson equation. Okay. So if you go for the this parabolic partial differential equation, it is transient heat conduction in a rod. Okay. So if you think of del T equals to alpha del 2T del x2 in one dimension, let us say that is the heat transfer, the unsteady heat conduction in a rod. That is the example of the parabolic partial differential equation. If you remember the boundary layer equation, x momentum equation, this boundary layer equation, X momentum equation, is also a parabolic partial differential equation. The wave equation, it is an example of okay. So here we have shown some examples. Suppose we have shown the wave equation and we have derived it that wave equation is hyperbolic. So this is the Laplace equation. It can be Poisson also. So we are just finding the values of A, B, and C, and we are finding the value of discriminant. So Laplace equation, we are showing that this is elliptic, and the equation, this is the unsteady heat conduction in a rod. We are finding the values of A, B, C, and we are finally concluding that this heat diffusion equation is parabolic. Okay, so this classification of partial differential equations in a CFD problem, this is the first step, and this is very much required. So you have to know the nature of the equation, that how the, based on that only you can decide that yes, it is a marching problem or it is an equilibrium problem. Based on that you can approximate the unsteady diffusion, you can approximate the different terms, unsteady term, convection term, diffusion term, etc., etc. Then here this classification can be done by using the method of eigenvalues also. So we are skipping it. So there are two types of problems based on the classification of the governing equations. So one problem is the marching problem. Okay, so it can be either initial value problem, or it can be initial boundary value problem, or it can be equilibrium problem. So the second picture which we are showing here, this picture and this picture, these two pictures, they are valid on a closed domain. Okay, so this is a closed domain where we are writing that this boundary gamma must be closed. So we are specifying the boundary conditions at every point of this boundary. Because of that, this is known as a boundary value problem. Okay, so we are showing this is a two-dimensional slab. Okay, and then we are writing the Laplace equation del square t equals to 0, and we are specifying the boundary conditions at all the boundaries. So there are, this is insulated, these two boundaries are insulated boundary. So these are the Neumann boundaries, and these two temperature is specified, T equals to C1, T equals to C2. So these are the Dirichlet boundaries. So at every point, every boundary, conditions are well defined. Okay, so we have to find the temperature within the domain here. So this problem can be solved analytically, experimentally, or by using CFD. So this is an example of an equilibrium problem. We don't need any initial condition because this Laplace equation, there is no time derivative. So this temperature, it is only function of x and y. It is not a function of small t. Now if you go for the marching problem, we are showing the example. What we do that in a marching problem, Hagen-Poiseuille flow is an example of marching problem. The problem which I was telling, flow through a pipe. So this is an example of a pipe. You know the initial condition, you know the boundary conditions, and you are moving towards the right side to get the new solution. Okay, so if you go here, these marching problems are either of initial value problem or of initial boundary value problem. So the domain will be an open domain. So if you see here, this is a closed domain. This is also a closed domain. So here what is happening, that this is the schematic diagram to explain the marching problem. So in a transient heat conduction problem or in a boundary layer problem, this is the initial data line where we know the initial condition at x equals to 0 or t equals to 0. Knowing the initial condition, and these are the boundary conditions, we are satisfying the boundary conditions, and we have to travel in the right side. So this is the direction of marching forward. So if we travel to the right side, knowing the solution here, we can find a solution. Suppose if temperature is unknown, if it is a heat transfer problem, knowing this temperature here, we will find the temperature here at this point, suppose, or at this line. Then using this solution and these boundary conditions, we shall get the solution along this line. So ultimately we can come here. So knowing the solution, so this domain is open. When we are given the problem, we don't know what is the temperature here, but we have to find out what is the temperature here. So you can think of, suppose this is a temperature distribution problem in a rod. Okay, so if I ask you now, the initial temperature of this rod, it was 10 degrees centigrade. After 1 hour, what will be the temperature. Now after 1 hour, we don't know what will be the temperature. So we have to march in time. We have to travel in time in the future direction. In time, we cannot move in past. We can move only in the future. So what is happening that we know the solution now. Using this solution, we can calculate what will be the temperature after 5 seconds. Using that solution, again we can find out what will be the temperature after next 5 seconds. Like that, we can calculate what will be the temperature after 1 hour. It means that knowing the initial solution, we are predicting the temperature in future. So we are moving in time from present to future. This moving is known as the marching. Okay, so this is marching forward. So parabolic partial differential equations or hyperbolic partial differential equations, these are examples of marching problems. In general, if an equation contains the unsteady term, not it is not always true, but most of the times it is true. If a problem is containing the unsteady term, it is likely to be either a parabolic equation or a hyperbolic equation. If an equation does not contain unsteady term, it is most likely to be an equilibrium problem. But this is not always true. Mostly it is true. Okay, so we have shown some details about this wave equation. There are two characteristics. Okay, as I was telling you that for the wave equation, b square minus 4ac is greater than 0. It has two real characteristics. So we have written here b square minus 4ac is greater than 0. We have two distinct slopes at every point in the domain. So we have two real distinct characteristics. So if you look into this wave equation solution, we are showing that this is one characteristic, this is another characteristic. These are having two different slopes, and this is a particular point. Okay, so this is the for the. So I think if you want to read more, if you want to know more about these things, there are two very good books. One book is by J.D. Anderson. Everywhere it is taught. John D. Anderson Jr. and J.D. Anderson, Computational Fluid Dynamics, Introduction to Computational Fluid Dynamics. This will be a very useful book. So that book you can purchase. Indian print is also available. And other book is by Tannehill, Anderson, Fletcher. So both of these books are based on the finite difference method. But these are very good books for the beginners. Okay. So you can first collect the book of Anderson, J.D. Anderson. So all these things are discussed in details and in very nice English. So you can read yourself and understand yourself. Okay. So similarly, we are showing it for the parabolic and the elliptic PDs. Now let us move to the boundary conditions. So for solving a CFD problem, we need the initial and boundary conditions. Okay. So if it is a steady state problem, we don't need any initial condition, but we need the boundary conditions. But in the CFD problem, always we need an initial guess. Whether it is a steady state problem or unsteady state problem, it does not matter. We have to put an initial guess. Otherwise, your calculations will not start. But in an unsteady state problem, if it is of IBVP type, you need initial conditions also, boundary conditions also. Okay. So the quantities, velocity, pressure, temperature, etc., they are known as the primitive variables. Okay. So density, there are two types of variables, primitive variables and flux variables. So by primitive variables, we imply rho, u, v, w, p, t, etc. There are 6 basic primitive variables, 3 velocity components, density, pressure, and temperature. Or you can combine these quantities and you can generate the flux variables. Okay. So our objective in CFD is to find out the primitive variables. And then there are 3 basic kinds of boundary conditions. The most common boundary condition is the Dirichlet type or the specified boundary condition. If we give the value of temperature directly, this is the Dirichlet boundary condition. If we give the heat flux, that yes, it is insulated or it is not insulated. But if we specify the heat flux, we actually imply that it is a Neumann boundary condition type. So this del phi del n, if we specify, then we talk about the Neumann or flux boundary condition. In finite element language, we say that this is natural boundary condition. In finite element approach, this Dirichlet boundary condition is known as essential boundary condition. If we combine the essential and the natural boundary condition, we get the Robbins type or the third type of boundary condition. Okay, so these three boundary conditions are required in CFD problems along with the initial conditions. Okay, so a CFD problem, it may not give you correct solution. So this problem must be well posed. So if there is an ill posed problem, you will not get correct solution. So well posedness requires three conditions. The solutions must exist, must be unique, and it must continuously depend on the auxiliary data. Auxiliary data such, these are known as auxiliary data represents the initial conditions and the boundary conditions. So I am showing one sample picture for flow past a square cylinder. Okay, so this is flow past a square cylinder. We want to solve it by using a CFD problem. So you can think of a building. Okay, so if you think of a building, air is flowing past the building. If you take a top view of the building, you will see that this is the roof of the building. Okay, so air is flowing around this building. So you can solve this problem by experiments. You cannot solve it by analytical approach, just impossible. You have to solve it either by experiments or you have to solve it by using CFD. So if you want to do by using CFD, what we have to do? Suppose air is containing the entire zone, but we have to specify that yes, I want to solve the problem up to within this boundary. Okay, so if this width of the building is d, I shall take maybe this is 20d or maybe this is 50d or 60d. So this much dimension I shall take within this rectangular domain. I want to use the CFD and I want to solve. So this need not be rectangle, this can be a square or this can even be a circular boundary. So this is the boundary. So in this particular problem, there are two boundaries. This is internal boundary and this is the external boundary, and this portion is filled with the fluid. Okay, so we have to specify the position of the coordinate system. So this is a two-dimensional flow problem. So there are four boundaries. Within all boundaries, we have to specify the boundary conditions. So this is an interface of fluid and solid. Here you have to implement the no slip boundary condition. By no slip, we mean that U will be 0 if the building is not moving. By no slip, we mean no relative velocity. So velocity components will be 0 and temperature will be same for the fluid and solid. Similarly, at the inlet boundary, we give the free stream condition. Free stream condition implies the air is coming with the free stream velocity. Whatever the velocity the air is coming with, that is known as the free stream velocity. This is a one-dimensional velocity, one-dimensional. Because of that, V will be 0, and this is the free stream temperature. So this is the lateral boundary or side boundary. So this is an imaginary boundary. All these boundaries, these are imaginary. We are just truncating it. So this is a real boundary. This is a real boundary, but this boundary is imaginary. So some student can take it, suppose we are taking it at 10D, somebody can take it 12D or 13D, it will not make a big difference. Okay, so here we shall specify the free slip boundary condition. By free slip boundary condition, we imply that this is a streamline. If we force it as a streamline, there is no flow across the streamline. If there is no flow across the streamline, then V will be 0. So V is this velocity. Velocity perpendicular to the x direction is V. So V will be 0 and shear stress is 0. Shear stress is 0 will give you del U del Y equals to 0. So these two are coming from the velocity boundary condition. This is known as the free slip boundary condition, and this is the zero temperature gradient boundary condition. Same thing will happen at the bottom also. At the right hand side, we are getting three boundary conditions: del U del X 0, del V del X 0, del T del X 0, and we force that the fluid is living at atmospheric pressure. This is the zero gauge pressure. So whatever we are discussing here, this is for the incompressible fluid dynamics. For the incompressible fluid dynamics, we take the gauge pressure. In compressible fluid dynamics, we always take the absolute pressure. So zero gauge pressure represents the atmospheric pressure. So we are representing pressure will be atmospheric at the exit. Now, if we summarize the governing equations, we have 5 equations for this particular problem. There is one continuity equation, one x momentum equation, one y momentum equation, one z momentum equation, and finally the energy equation. There are 5 equations. We can calculate 5 unknowns. These unknowns are Momentum equations will give you the velocity components. Continuity equation will give you the pressure, and energy equation will give you the temperature. What do we mean? We mean that after defining the domain, we have to discretize the domain. We have to generate the nodes here. How we can generate the nodes? You can draw a vertical line. You can draw many vertical lines, and we can draw many horizontal lines. Okay. So if you draw many vertical lines and horizontal lines, only not overlapping, then intersection of one vertical line and one horizontal line, it will give a node. Okay. At that node, you have to write these equations. So you will have many nodes. So at every node, you will have 5 unknowns: density, 3 velocities, 1 temperature. So there will be 5 matrices: 1 matrix from continuity, 1 matrix from x momentum, 1 matrix for y momentum, 1 for z, and 1 for the temperature, and you have to solve it. Okay. So these are the boundary conditions. And this CFD, you have already defined it, that what is CFD? The numerical approach of giving approximate but high accurate solutions. And these steps we have already defined it. Okay. So we need an oil post problem. Okay. Then this mathematical modeling, everything we have discussed it. So discretization, mesh generation. Okay, and these are the basic discretization techniques. So thank you for attending it. Thank you for listening to me. So we this first part ends here. So we close
Yes,
this
sir.
session.
Yes, sure, sure, sir.
Okay.
Okay.
Okay, good, sir. Thank you.
Okay. Okay.
So, hello.
Hello. Yeah.
Okay, sir. So thank you so much for informative session, sir.
So
Next,
I shall start
so
it around
Professor,
1 p.m.
yeah, sir, Professor
The
Tiwari, if
second
you want to
session.
add something.
Yes, yes, sir. Sure, sir. The second session will start at 1 p.m., I think, sir.
Okay.
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 Second
Thank
session
you.
is the
Okay, sir.
same. Dr. Sen will start at the 1 p.m. Okay.
Uh, okay.
Okay.
Thank you.
Thank you,
Okay,
sir.
sir. Okay, sir.
Okay. Thank you.